So the last little section that we need to discuss concerning molecules and the drawing of molecules and then predicting their behavior would be bond polarity. Now, as you can see on the screen there, we have an HCl molecule, and the diagram right below the molecule, you see something that looks like a funny S with a plus and a funny S with a negative. Now, what that means is the Cl is more electronegative, so in forming that bond, it is going to pull the electrons towards it, making the Cl slightly negative and making the H slightly positive. So you're setting up two poles in the molecule. So this HCl molecule would be considered polar. It's got a positive end and it has a negative end, and you could look up the electronegativities and figure out whichever one has the highest electronegativity is going to be the more negative part in the bond, and whichever one has the smallest electronegativity is going to be the more positive in the bond. So really then, Cl kind of has a greater share in of the bonding electrons than does hydrogen. Now what this will do is it will make certain molecules soluble in water, because water is a polar solvent. So if HCl is polar, then when you try to add it to water, it will dissolve in water, and then other things not soluble. So that's one use for this idea of bond polarity. Now, when we take a look at molecules, entire molecules that are made up of multiple atoms, we look at the symmetry, the three-dimensional symmetry of the molecule. So you really have to picture these molecules as if they're put together with a molecular model kit. If the molecule is asymmetric, meaning you can't really cut it down the center and have it fold upon itself, so it's asymmetric, then the molecule itself will be polar. If the molecule is symmetric, then the molecule will be nonpolar. So if it kind of looks like the whole entire molecule all the way through the molecule is essentially the same, then you get a nonpolar molecule. The polar bonds in the molecule can actually cancel each other out, so the net result is a nonpolar molecule. Now here's a picture of water, and as you can see, water is not symmetrical, and being not symmetrical means the water is polar. So you can probably cut it down the center vertically and the two sides will fold, but if you try to cut it horizontally through the oxygen, the top and the bottom are quite different, so you get a polar molecule with water. Now CCl4, and it's drawn three-dimensionally there, so you have to picture the three-dimensionality of the CCl4 molecule. That CCl4 molecule is nonpolar. That is, all of those bonds are pulling equal and opposite as shown by the arrows there. So what you get is a net nonpolar molecule. So polarity of molecules is not only based on electronegativity, but it's also based on the position of the atoms and the three-dimensional symmetry of the molecule. Now, as I said before, you use bond polarity really to predict how things will combine in solution. So oil happens to be a nonpolar molecule, water happens to be a polar molecule, so therefore those two will not mix together, and you'll end up with layers whenever you mix water or try to mix water and oil together. This leads us to the statement like dissolves like. That is, polar substances will dissolve polar substances, nonpolar substances will dissolve nonpolar substances, and this idea has led to the development of detergents such as Tide, and has also led to the development of stain removers such as Shout. So these stain removers then have the same polarity as the substance they're removing, and it's possible for a substance to have two different ends, a polar end and a nonpolar end, so that particular substance then can mix with both polar and nonpolar stains. So that's a direct use of this whole idea of bond polarity.